Okay, I think we can start. So today's speaker is Riku Anttila from Jyväskylä, and he's going to tell us about a counterexample to Kleiner's conjecture. Thank you, Riku.
Thank you for the introduction, and thank you very much for the organizer for giving me this opportunity to talk here. And thank you also very much for the invitation to this program. So far, it's been really amazing time. Okay. In this talk, I will talk about my joint work with one of my supervisors, Sylvester Eriksson-Bique. And the topic is Kleiner's conjecture. Okay, so to give you a little bit context, I work in a field called analysis on fractals. So for me, a fractal is some kind of very complicated geometric object with some kind of self-similar structure. So here I have three examples, very common ones. The Sierpinski gasket, Sierpinski carpet, and the Merger sponge. Many of you probably have seen this at some point. If in the case you haven't, and just for a reminder, for example, the Sierpinski carpet is constructed as follows. First, I have a standard square in the plane. I remove the center square, so I'm left with 8 squares. For each 8 squares I have left, I remove the center part. And now I have 64 small squares left, and then I iterate infinitely many times. This produces a fractal, which is called Sierpinski carpet. Okay, and the Sierpinski gasket, you do pretty much the exact same thing with triangles, and Menger sponge, very similar construction, but with cubes. So the topic I will discuss today is Kleiner's conjecture, and in particular, the goal of the talk for me is to present our result with my supervisor Sylvester, which is a counterexample to Kleiner's conjecture, and hopefully give you some insight why it actually works. That's the plan. All right, so to give a little bit more context what Kleiner's conjecture is about, I will first give you just a very vague statement what it is about. I will give you at some point later a more exact statement. So Kleiner's conjecture is a problem in quasiconformal geometry of self-similar fractal spaces and also boundaries of hyperbolic groups. Well, in this talk I will focus on the fractal part. So this means, in this context, that I study quasisymmetric homeomorphisms between metric spaces. So this is a very, this notion was, Damaris introduced this notion in her talk a few weeks ago, if you remember. So roughly, quasisymmetry is a homeomorphism which has bounded distortion, and it means that it satisfies this kind of inequality. So this means that it preserves ratios of distances rather than preserving the distances. So geometrically, it means that, or I like to think about quasisymmetries, is that they preserve shapes, but not necessarily their sizes. So what this, for example, means, what quasisymmetry cannot do is, for example, the following. So if I take a very perfectly shaped, my drawings cannot do, I take a perfectly round ball in the metric space. What it cannot do is to make it infinitely flat. So for example, one ball gets mapped like this, other ball like this, other ball like this. So there has to be some kind of bound that how flat it can make round objects. So this is what a quasisymmetry means. Okay, so to support this intuition I present you, I have two examples, one of them which is a quasisymmetry, another one is not. So the first one is called radial stretch. So it's the one in the top. So what it does is that how it behaves here is that I take a ball center at the origin, and it makes the exact same shape of ball, but with square radius. So it preserves the shape of this ball. And I also can show that this is actually a quasisymmetry. And the other one below, what it does, it also stretches, but only to the direction of the real axis. So it makes round balls really flat. If it's really large, it becomes more and more flat. So it is not a quasisymmetry. So a quasisymmetry is a homomorphism which preserves shapes but not size. Okay. So a bit more concretely, Kleiner's conjecture is about some kind of quasisymmetric uniformization problem on self-sigma fractals. So what quasisymmetric uniformization means, or in general uniformization, is about, so I have some, let's say my favorite metric space, which is for some reason really horrible. Then I ask if there is a better representative of it. So in this case, I ask, is there a somehow canonical and more nicer version of it? So, right, I can do this. So in this here, I have cos snowflake. Cos snowflake is a fractal which has it is a one-dimensional curve which has infinite length, and also it has it contains no non-constant rectifiable curves. So it is a really horrible space. But it is quasi-symmetrically equivalent to this smooth curve, or this smooth line, which is much more nicer. So if I want to study let's say quasi-conformal geometry or like anything, I prefer to have this smooth curve instead of the snowflake one. Okay. So this is one simple example of a quasi-symmetric uniformization. But this previous one is a little bit quite trivial and uninteresting. So here I have a little bit more interesting one and much more non-trivial one, and this is called harmonic Sierpinski gasket. So on the left I have the regular Sierpinski gasket, and so what this uniformization is doing is that on the Sierpinski gasket there is a more or less a canonical way to construct a Dirichlet form, and Dirichlet form is like a kind of generalization of the bilinear form, bilinear energy form of this type. So there is some kind of very natural construction of a Dirichlet form on the Sierpinski gasket. But the problem is that in the triangle one, the geometry doesn't really provide good enough information about it. So for example, the Lipschitz functions don't really work there. That's a pretty big problem. But then Kikami noticed in the 90s, using the idea of Kusuoka, that turning the Sierpinski gasket into this harmonic Sierpinski gasket, we have much more tools available. So it is a more appropriate geometry or geometric environment to study the Dirichlet form. And later, Koskela and Zoe noticed that if I introduce some more classical constructions of general metric spaces, meaning like Sobolev spaces and gradients and so on, then those can be used to reconstruct the natural Dirichlet form, but only on this harmonic Sierpinski gasket. So the same construction on this triangular Sierpinski gasket gives me nothing. But if I do it on the harmonic one, it actually gives me something. So this means that if I'm interested in the Dirichlet form of the Sierpinski gasket, I'd rather study the harmonic one. So this is, again, a particular case of a uniformization problem.
I have a question.
Yep.
But if you take another object which is quasi-symmetric to the Sierpinski gasket, will it give you the same? Like if you take different quasi-symmetric copies, do you get the same, like Sobolev spaces, for example?
It depends how you define Sobolev spaces.
Right.
Like Newton's Sobolev space here gives me this, so the Dirichlet form, which is natural for the Sierpinski gasket. But if you do it on that one, Newton's overall space on that one, that shouldn't give you something. So that it doesn't give you the something.
Okay.
So it is really a good uniformization. Okay. Yeah. Any more questions? Okay. So this particular uniformization has nothing to do with Kleiner's conjecture. So this I will not return. Just to clarify. Okay. So now I introduce a really important concept in quasiconformal geometry and also in analysis. This has appeared in the talk of Damaris a few weeks ago. Sorry. So to define modulus, I need a metric measure space, and I define modulus between two sets. So I have two disjoint sets, which are usually compact, and I look at all the rectifiable curves between them, and all Borel functions which integrate to at least one over all those. And then I take the infimum of the p integrals of these densities. So this is the definition of modulus. So it is not super important what this definition exactly is, what it exactly means. But the point I want to make is the following: is the notion of a conformal modulus. In particular, in Rn, n modulus is scale invariant. So for example, here I have a modulus over annuli, which means that I take all the rectifiable curves from the inner boundary to the outer boundary. Now if I compute the modulus, I notice that only for p equals to n, this value is scale invariant. So it doesn't depend on the radius. But for every other p, there is some contribution also from the radius. So this makes n modulus in Rn very special. It is a really nice connection between geometry and analysis. Another example in the complex plane is that a modulus of a rectangle. So, see this one? So I studied all the rectifiable curves here and here. So for this, I can compute that the optimal density is actually just a constant. And again, I will see that the modulus is scale invariant only for p equals to 2, like in the previous case. So an interesting corollary of this is that I can use this conformal modulus, and two modulus in this case, to show that there is no conformal map in the complex plane that maps a square to a rectangle so that it also preserves the vertices. And the reason is that, let me draw here. So by vertices I mean that it maps these points to these 4 points. So there is no conformal map which maps a square to a rectangle while preserving vertices. And the reason is that the modulus from, so if there was, then let's say that this point and this point are mapped like this. And in this case, this whole line has to be mapped here. And with the same argument, this whole line must be mapped here. So because conformal maps preserve modulus, and the modulus from here to here is just 1, according to that computation, and from here to here is not equal to 1, then this shows that there cannot be such conformal map. Okay. The point again is that conformal modulus is a really good connection between analysis and geometry. Okay. All right, so back to Kleiner's conjecture. So now I'll give you a little bit more concrete statement what Kleiner's conjecture is about. So Kleiner's conjecture asks, if I have a self-similar fractal, when can I say that it is quasi-symmetric to a Lerner space? So what is a Lerner space? So Lerner spaces were introduced by Heinonen and Koskela in the 90s, and it is basically an abstraction of conformal modulus. So it has two conditions. First, it has to be Q-Ahlfors regular, which means that the Q-Hausdorff measure of a ball of radius r has to be uniformly comparable to r to the power of q. And then there are these Lerner estimates, which says that the modulus is controlled by this value called relative distance. So if this looks very weird, then you can think that this is just a constant it measures the distance of two sets in a scale invariant way. So that is why we have divided by the diameter here. So if we go back to this example, or this one, then if I compute the relative distance of this set and this set, it gives me, so distance is b and the diameters both are a, so the relative distance is just a over b, which is, I think it's 1 over the modulus. Okay. So again, in this case we have all these non-separates. So why this is interesting is that what Heinonen and Koskela essentially showed that Lerner spaces admit similar theory of quasiconformal geometry as the Euclidean space. So this is a very good kind of a generalization of conformal modulus into more general metric spaces. So this is the point. And also, this gives motivation for Lerner spaces and Lerner spaces Kleiner's conjecture. Because if you are quasi-symmetric to a Lerner space, then that means that you have the same quasi-conformal geometry as the Lerner spaces.
When you are talking about quasi-conformal geometry, so what kind of results should one have in mind? So for instance, you said this big meta theorem. So what does it include?
So for example, if I have a quasi-conformal map from Rn to Rn, then I can upgrade that to quasi-symmetry, for example. So that is, basically the result of Heinonen and Koskela is a generalization of it. So quasi-conformal mapping it's a seemingly weaker notion of quasi-symmetry, basically. But with nice geometry, particularly in Lerner spaces, I can always upgrade quasi-conformal map to a quasi-symmetry.
When you say you can when you say you can upgrade quasi-conformal to quasi-symmetry, what do you mean by that?
I mean, I can say
quasi-conformal implies quasi-symmetry. That's what you're saying. Okay.
Or at least, if the sets are compact, then you can have local estimates at least. If they are unbounded, then you should be able straight away to say that they are quasi-symmetric.
And for Lerner spaces, quasi-conformal implies quasi-symmetry? Okay.
Sorry, I have also a question.
Yeah.
Are there easy examples where of spaces where the second condition fails? The Lerner estimates.
Yes, I will show you.
Okay.
Some
simple examples that are not your counterexample.
Yes.
Okay.
Well, first I will show you some examples. So first of all, the Euclidean spaces where n is at least 2, they are Lerner. They are basically the models of Lerner spaces. But also Carnot groups are Lerner spaces, for example, the Heisenberg group. There are also examples in hyperbolic geometry, the so-called Wall-and-Pajot buildings. But there are also fractals. Lots of spaces are fractal spaces. So Laakso showed that for every exponent there is a Lerner space. In particular, it is certainly possible that the fractal is a Lerner. But to answer your question, Sierpinski carpet, at least with the Euclidean metric, is not Lerner. It is Q-Ahlfors regular, but it is not Lerner, and it fails in the most miserable way possible. It says that the result of Q-Poincare and Peugeot, and also this is also included in Mackie and Tyson's book. It says that the modulus of all non-constant curves in the Sierpinski carpet is 0. Okay, so there is no control, or no geometric control over modulus. Okay, so this calls for uniformization. So it is not Lerner, but maybe it can be uniformized into a Lerner space. But this is an open problem, and it is a really hard open problem. This is one of my favorite open problems, but anyway.
And what about this harmonic? So there is
Cascade. Okay, so to be a learner, there are some topological obstacles too. So you have to be, first of all, connected, and you can't have cut points. Okay, maybe I can go back. So you can't have cut points. So Sierpinski cascade has cut points all over the place. The cut point meaning that if I remove the point, then it disconnects it, or at least locally disconnects it. So that is not possible for Lerner space. In particular, this you cannot uniformize in the Lerner space.
Are there multiple logical abstractions?
Well, it is a hard question. I mean, like, well, our counterexample has one such obstacle. It is a bit different one. Okay, I think I was here. Yes. Okay. So I think the next few slides are going to be a little bit heavier. Unfortunately, I have to introduce some notions, which all of them are not that easy to understand what's the point, but I do my best. Okay, so maybe I can erase this. Okay. So as we saw last slide, modulus, at least the regular modulus, does not work for Sierpinski carpet. So instead, we can introduce a notion of modulus that actually works. And this is the object called, analytic tool called combinatorial modulus. So what does it mean? Basically means that I introduce a reasonable notion, the generalization of dyadic cubes. So I have the example for the square. Okay, so for the regular modulus, I looked at all rectifiable curves from the left side to the right side, and looked at all Borel functions that integrate to at least one. For the discrete modulus, or the combinatorial modulus, what I instead do is that I discretize my space. So here I take a covering. In this case, it has 4 parts, or 4 members. And then I change the curve a little bit. Let's say I take this curve, and each member in the covering is given some weight. So weight means that if I have the covering, well, there I have CK, so in this case it's C1. C1 is, say, A1, A2, A3, and A4. And I have a weight function from the covering. Okay. Now I look all curves, not only rectifiable curves, now I look all curves from the left side to the right side. And I look at the densities, so that if I take any curve in the curve family, then I look at all the members in the covering that intersects that curve, and they have to sum up to at least one. So this is basically like a discrete path integral.
The curves you are looking for are real curves. So these are not discrete curves, these are really continuous curves.
Continuous curves. Well, usually they give you the same thing. But if I have any discrete curve here, I hopefully can do that. I take some point here and connect it to here, like this. Usually they give you the same thing. In all reasonable cases, they should give you the same thing. Okay. So these are the ways I look, and the more discrete modulus is then the infimum of all the discrete Q integrals of the densities. Okay.
But what are the dyadic cubes?
Right.
From this example, I understand.
So in general, if I have some random metric space, and in this discretization context, I would like it to be a compact space, a compact metric space. So what I do is that I just take some reasonable covering. They are usually balls. Some balls of almost same radius, hopefully, and I don't want them to intersect too much. So it's probably looks something like this.
But you fix some covering for each cable.
Yes, exactly. And you can show that in all reasonable cases. If you are metric doubling, then it shouldn't matter which you choose. Okay, so this is a very straightforward discretization of modulus. And then there is an analogical notion of Q-Loewner property for the discrete modulus, which is the combinatorial Q-Loewner property. So this was introduced by Heinonen and Kleiner, and it is basically exactly what it sounds like. So I have Q-Loewner estimates for the discrete modulus. And the reason I write the large K is that if I have only 4 members like this and I take 2 very small sets, maybe even inside the same member, then this covering doesn't distinguish these two. So the covering has to be the members have to be much smaller for this to work.
So K depends on E.
Yeah. Now the good news is that Heinonen and Kleiner showed that Sierpinski carpet, which didn't satisfy the Q-Loewner property, now satisfies this discrete Q-Loewner property, or the combinatorial Q-Loewner property. And a really useful result is that if I have a Q-Loewner space in the beginning, then these two different notions of modulus actually give me the exact same thing. And you can also say the same thing with much weaker assumptions. But anyway, for Q-Loewner spaces, this is true. And one really good thing about this construction is that the combinatorial Q-Loewner property is quasisymmetry invariance. Meaning that if one of the metric spaces, which are quasisymmetric, the space is combinatorial Q-Loewner, then all of them are. So this at least indicates that we are doing something right. now I will give you the precise statement of Kleiner's conjecture. It says that if I have a self-similar fractal which satisfies the combinatorial Lerner property, then it should be quasisymmetric to a Lerner space. Okay, well, now I will give you some motivation why anyone would think this is true and why this is a natural statement. So first of all, if there exists the hypothetical Lerner structure exists, then in that case, first of all, why is combinatorial Lerner? If why is Lerner, then it is combinatorial Lerner. It follows from the previous statement I just said. But because combinatorial Lerner property is quasisymmetric invariance, then so is X. But the reason why it would be really natural to expect this conjecture to be true is that in some way it should be possible to extract geometric information from the hypothetical Lerner structure, in some sense reverse engineered from X using the combinatorial modulus and the combinatorial property. So what I mean is that. So this is a hand-waving argument I came up with for this talk. It could be that this makes absolutely no sense in reality, and it could be that the Kleiner himself didn't even think about this and thinks this is complete nonsense, but I tried to give some insights why I think that this is a natural statement. So I have my horrible metric space X. Can you see this? So X is just some metric space which is quasi-symmetric to a Lerner space. So it can be very horrible. It can be a small space. So it is something like this. And then I have my really nice smooth space. Really nice smooth Lerner space. Okay. So using combinatorial modulus and the combinatorial property, I should be able to, or I am able to extract information of modulus here because of the. This is too low. Can you see? Yeah. So the discrete modulus in X, it is comparable to the modulus in Y. But then modulus, Q modulus, well, it is just an integral over the Hausdorff measure in this case. So this is some integral over the Hausdorff measure.
Sir, are you assuming Q is your self-similar fractal group?
Sorry?
Which is, are you assuming that X is your Q CLP, self-similar fractal, which is Q CLP?
Yeah.
Okay.
Yeah. So X is just some horrible metric space with this quasi-symmetric Lerner space. Okay. So from this argument, I can gain information of the integrals against the Hausdorff measure using the discrete modulus. And if I somehow have enough information about the integrals against Hausdorff measure, I should be able to gain information about the Hausdorff measure. And because this is an alpha regular Hausdorff measure, I should be able to figure out some information about the metric.
But where? So this HQ on?
So HQ is here.
On Y?
On the really nice mode structure of the Lerner space. And this also should be in the Y. So at least for me, this kind of chain of arguments, this hand-waving level, makes sense.
So what should it be? What should it convince us about?
So here I am arguing why if this exists, then I should be able to gain information about the structure of it. Only looking at here, I should be able to extract information on here.
So if it exists, then you can...
Yes, that is it. If it exists, I should be able to extract it. But then,
just some questions. So in this similar fractals, so they are not, there you don't have any assumptions about the Hausdorff dimension. So they can be much higher.
yeah. So at least using this argument I showed you, at least I'm like this hand wave level convinced. For me, it's convincing that I should be able to gain information about the level structure. But now the question is that if I theory don't know that this exists, then does this give me something? And Kleiner's conjecture says that it should be possible. Okay, I think I have one more notion I have to explain is the Q-Ahlfors regular conformal dimension. So it is a general result by Carrasco-Piaggio, follows from the general result of Carrasco-Piaggio, that if I have a Q combinatorial space, then Q is equal to the Q-Ahlfors regular conformal dimension, which is defined as the infimum of all the Hausdorff dimensions of the metric spaces that are quasisymmetric to my space and are Q-Ahlfors regular. So what this is asking is that how much can I lower the Hausdorff dimension? Okay, and Kleiner's conjecture actually has a much more simpler way to express it. So if I have a self-sigma fractal, which is combinatorial, then there must be some quasisymmetric version of it which has minimal Hausdorff dimension. So
that's an open line.
Sorry?
Is it open or is it also disproved?
So this is equivalent to Kleiner's conjecture. So it is not true.
So it is wrong.
It is wrong.
So this would be automatic, yeah? So such a space would automatically be Q-Ahlfors below, no?
Yes. So this more or less comes from the fact that discrete modulus and the continuous modulus are comparable in the correct geometric setting. And if I attain the conformal dimension, Q-Ahlfors regular conformal dimension, then that is a correct geometric setting that is true. I think, yeah. Okay, so this part now concludes the part. Me explaining what is Kleiner's conjecture. So, any further questions?
Sorry, but this corollary, this is true. Yeah? This is corollary not of the conjecture.
Yeah, this has nothing to do with Kleiner's
So
conjecture.
it's always true.
Yeah, it is always true. So Carrasco-Piaggio's result is a characterization of Q-Ahlfors regular conformal dimension. It says nothing about the attainment, only about what the value is. Okay. So formally, I simply erase this. Here on, I will talk about our result, in particular our main result, which is the counterexample to Kleiner's conjecture. And our counterexample is constructed as a limit of graphs. So here I have the first three. So this is, in reality, this is going to be an infinite sequence of graphs. And the main theorem is that this space satisfies the combinatorial property, but it is not quasisymmetric to any Lerner space. And equivalently, it does not attain its Ahlfors regular conformal dimension. So now my goal is to explain, like very roughly explain why this is the case. So first of all, in our paper we introduce a general construction of fractal spaces using these kind of graphs. And this construction is called iterated graph systems. It is basically a discrete iterated function system. So that's where the name comes from. So here, the first step is to fix some graph, some connected graph, and something that we call Lewin rules, whatever they are. So in this example, I fix my graph to be this one. So the next step is I replace each edge in my first graph with the first graph, and I obtain this kind of disconnected graph. And then according to the predetermined gluing rules, I just glue them together. So in this particular case, what the gluing is that I have the first graph here. So for example, here, I replace these three edges. Then I look at all the edges that has a common vertex with this one. So in this case, this one, so it's these three have a common vertex, then I glue them together here. And the next step is to iterate this construction, or this replacement and gluing. So here is the third graph. And I iterate, so I get an infinite sequence of graphs.
Self-similar just means that the small graph appears.
Yeah, so this is self-similar. Okay. And the last step to obtain a limit space is to take an appropriate Gromov-Hausdorff limit. So in this case, I scale my path metrics and I take the Gromov-Hausdorff limit.
And do you scale it how?
In this case, so the distance from here to here is 4. Mm-hmm. Then I take, so in this case, Dn is 1 over times n by the path metric. So it normalizes the distance at each level from here to be 1. So this is a metric space for Large diamond. This is what this exact picture which is embedded into the space, into the plane. So this is not exactly the Large diamond. This is a snowflaked version of it. So this was introduced by Lang and Plot, and Larks are around the same time. Okay, so this is our general construction. The main examples are a little bit different. So in our proof, we consider two limit spaces of iterated graph systems. And the main difference from this to that case is that this time we glue at 2 points. So maybe I can go here. So the first picture is this, and the second one, I replace these two. So now I glue this point to this point and this point to this point. So this is much more complicated to draw. This, I'm not sure if it's planar graph. At least the high level graphs are not planar, but the point is that these are really hard to do. Anyway, this gives me a well-defined limit space.
And where do you, so this is the the two edges on the left.
So this one is this one, and this one is this one.
And also say the upper.
This one?
Yeah. So where is it?
So it's so I do this to this and this to I guess this and this. And also I have this one, so it's also good to this.
So the balance growth much faster.
Sorry?
So there are much more branches now.
Yeah. But the degrees are bounded. Okay. And the second example is exactly the same thing, but now I have one extra edge here. So the goal now is to show that this second example does not attain its Ahlfors regular conformal dimension. And to show it, I use the following general result. It says that if I have any subset, or any metric space and any subset of it, it satisfies that they have the same Ahlfors regular conformal dimension. And the smaller subset is a porose subset. The porose subset means that the set has a lot of holes. So for example, well, Sierpinski carpet is a porose subset of the square, and how you actually define it is that whenever you take a ball and you look at how much this ball intersects the smaller set, then there is a constant size of ball in the component. So there are a lot of holes. And now the punchline is that a subset, a porose subset, so a subset with a lot of holes, should have a strictly smaller dimension. So in the correct geometric environment, this is true. And using this fact, I can show that. So using this fact in the correct way, I can show this. All right. Okay, so there are a few preliminary results. So first of all, this embedding is a bi-ellipsis embedding onto a porose subset, or you can think that this is just a subset. So to see why it's a porose subset, well, you see that if I think this as a subset of this other guy, then I have first of all a hole here. But at the second scale, I have also holes here. And when I go even deeper and deeper, I see that I have holes everywhere. Because I have basically removed a big part, or even, it is essentially I have removed balls at every scale. So from this argument, I can show that this is a porose subset. It has a lot of holes. The second one is that this first unit space, this is actually a 3/2 Q-Loewner, and its Ahlfors regular conformal dimension is 3/2. So this is a Q-Loewner space. And this more or less was already known. This is a very close variant of Laakso's construction, which produces Q-Loewner spaces of any dimension. And it also falls under the construction of Jyväskylä and Kleiner's inverse limit construction, if you are familiar with that.
Is there some special property of the graph which appears there? And so there's no much difference.
So maybe, so the main thing about this guy is that like important assumption in the Jyväskylä construction is that they are kind of their limits are it is a projective limit in the sense that if I project it like this onto the interval, so this is a simply shown up and it does not collapse any edges. But if I have it like this, then it collapses this edge. So this is the primary difference. And this is the main reason why Jyväskylä and Kleiner construction cannot produce the second one. But nevertheless, this is combinatorially Lerner. It is more or less about the fact that combinatorial Lerner property is very general and very generic property for self-similar fractals. So it is a bit tedious to prove it, but anyway, nevertheless this is true. And now to use the punchline, which said that a porous subset or a subset which has a lot of holes should have a strictly smaller dimension. Now I have to prove that this has Q-Ahlfors regular conformal dimension exactly equal to 3 over 2. Okay, to show it, what we essentially did was that, or what we can do is that if I just make this middle part smaller and the even size of epsilon, this decreases the Hausdorff dimension, and by making it arbitrarily small, it goes arbitrarily close to 3 over 2. But on the other hand, it cannot be more than, or it can't be decreased below 3 over 2 for the reason that it contains a subset which has conformal dimension 3 over 2. So from this argument, it follows that the Q-Ahlfors regular conformal dimension of the second limit space is exactly the same as the bigger one. Well, there is a technical detail to show that this is a quasisymmetry. We didn't show it in our paper. There is some other work where we are doing it. And the argument we use are also to put 0 here. But the reason why this is a quasisymmetry is that no matter how small this is, the middle part is, the distance from the left side to the right side is still preserved. So using this fact, the kind of like the distortions don't, like there is essentially only one distortion which matters for each pair or for each pair of pairs. Okay, so this concludes the proof. So just to summarize, what Kleiner's conjecture says is that every self-similar fractal which satisfies the combinatorial Lerner property is quasisymmetric to a Lerner space, or equivalently they attain the Q-Ahlfors regular conformal dimension. And our main result is that this is actually not true, is not always true. We constructed a self-similar fractal with this 3 over 2 combinatorial Lerner, but it is not quasisymmetric to any Lerner space. And the outline of the proof that this embedding is a bi-Lipschitz embedding onto a porous subset, and they have the same Q-Ahlfors regular conformal dimension. So this is this is not a topological obstacle, but this is one way the attainment problem can fail, or Kleiner's conjecture can fail. Okay. So the last thing I want to mention that all counterexamples at the moment are topologically one-dimensional. This is because our construction exclusively produces topologically one-dimensional objects. And at the moment, there are no counterexamples with the boundaries of hyperbolic groups, and it is still open for this Verbitsky counterexample response. So all of these are quite restrictive, especially the first one shouldn't be a real obstacle, but I have tried. At the moment, no ideas. And there are a lot of examples where the conjecture is open. Borden and Kleiner and also Weiss later show that there are many boundaries of hyperbolic groups which are combinatorial Lerner, but are not known to be quasisymmetric to Lerner. And we also have some other results which says, roughly speaking, says that symmetric fractals with reasonable amount of connectivity are also combinatorial Lerner. Okay, so that's all I wanted to say. Thank you for your attention.